own heart. You might know me as Sabrina the Teenage Witch.
I just made up that stuff so Morgan would leave.
Oh, I get it. No, I don't.
Sabrina, I'm no expert on magic, but it looks to me like you're under a spell.
Spell?
You're a witch, remember?
Oh my gosh, you're right! Hey, I never have to go shopping again! Although I play a student with some extra special abilities, I'm here to tell you that in real life, there are no shortcuts to your education. I feel like a Porsche.
I don't drive a stick.
You do now. Learning math, science, and technology will help you work towards your dreams. In this episode of NASA Connect, you'll learn how awesome our sun really is. You'll observe NASA engineers and researchers using math, science, and technology to explore the sun-Earth connection. In your classroom, you'll do a cool hands-on activity as you chart the sun's solar cycles. And using the instructional technology activity, you will explore the web to discover even more about the sun-Earth connections. So stay tuned as hosts Jennifer Pulley and Dan Giroux take you on another exciting episode of NASA Connect.
Hi, welcome to NASA Connect, the show that connects you to math, science, technology, and NASA. I'm Dan Giroux.
And I'm Jennifer Pulley. Welcome to the Maryland Science Center here in Baltimore, Maryland, home of the Hubble Space Telescope National Visitor Center. Today's show is about
the sun.
Did you know that it would take more than 1 million Earths to fill up the sun? And get this, more than 99% of all matter in our solar system is in the sun.
It only takes about 8 minutes for light from the sun to reach Earth, and as big as our sun is, it's only considered an average-sized star.
Here's another interesting fact. In 1989, the sun actually knocked out power in Canada.
You mean the sun stopped electricity on the Earth?
That's right. We'll tell you later how it happened.
In the next half hour, we hope to give you a better appreciation for how the sun works, how it affects us here on Earth,
and how NASA researchers are studying the sun.
Right, but before we continue, there are a few things you and your teacher need to know. First, teachers, make sure you have the lesson guide for today's program. It can be downloaded from our NASA Connect website. In it, you'll find a great math-based hands-on activity and a description of our instructional technology components.
Kids, you'll want to keep your eyes on Norbert, because every time he appears with questions like this, have your cue cards from the lesson guide and your brain ready to answer the questions he gives you.
Oh, and teachers, if you are watching a tape version of this program, every time you see Norbert with a remote, that's your cue to pause the videotape and discuss the cue card questions. And now, back to the sun. Dan, a little more on my right, please.
Oh, sorry.
Thank you. The sun is our nearest star. It provides us with warmth and light. We all know that the sun is important to life on Earth, but few of us have been given a good description of the sun and its composition.
Our sun is an average star, similar to millions of others in the universe, but it's a big energy machine. If you could capture the energy the sun produces in 1 second, that would supply the United States with enough energy for the next 13 billion years.
Where does the sun's power come from?
Good question. The basic energy source for the sun comes from nuclear fusion, and this is when mass particles combine and tons of energy are released. The core, or innermost part of the sun, is made of hydrogen. The sun is so dense, and its size is so large, that light released from the core takes about 100,000 years to make its way to the surface. If the sun were to stop producing energy today, it would take 100,000 years for significant effects to be felt at the Earth. Scientists think there is enough hydrogen on the sun to continue producing energy for another 7 billion years.
For many centuries, little was known about the sun. However, in the early 1600s, the Italian scientist Galileo used a telescope to take a closer look at the sun. He found dark spots that occasionally appeared and drifted across the sun. He also noticed that the dark spots on the sun's surface were constantly changing. These are called sunspots.
What are sunspots?
Let's find out. NASA Goddard's Dr. Eric Christian has some answers for us at the Naval Observatory. It's a blast.
Thanks, Dan. The sun is a fascinating place and a brilliant object to observe. We observe the sun through telescopes like this one here at the Naval Observatory in Washington, D.C. But satellites help us too. To get a better understanding of the sun, let's look at its different parts. The visible surface of the sun, that which we can actually see with the human eye, is called the photosphere. Temperatures here are around 6,000 degrees Celsius. The next two outer layers of the sun's atmosphere are called the chromosphere and the corona. The corona is actually hotter than the photosphere at temperatures of 1 to 2 million degrees Celsius. The corona is visible to the naked eye during solar eclipses. Remember the dark spots, or sunspots, that Galileo studied with his telescope? Well, sunspots are dark, cool areas of the sun's surface where charged particles are emitted. The sunspot only looks dark relative to the brightness of the rest of the sun, but it's still pretty hot, 4,000 degrees Celsius hot. The average sunspot is about the same diameter of the Earth. Sunspots generate some of the most violent storms in the solar system. When a sunspot erupts, we call this a solar flare. Solar flares are some of the biggest explosions in the solar system. When a solar flare occurs, gas heat of more than tens of thousands of degrees and energy surpassing billions of atomic bombs is hurled out from the sun. Another type of explosion is the CME, or coronal mass ejection. These explosions can reach speeds of millions of kilometers per hour and can reach the Earth in just 3 days. Both solar flares and CMEs can be very disruptive to human activity on Earth and in space as these storms, we call them solar storms, travel to the Earth.
You know, Dan, just like meteorologists use satellites to predict weather here on Earth, NASA uses satellites to predict solar storms.
Wait a minute. You're saying that in the future, we'll talk about solar storms like we talk about storms here on Earth?
We sure will.
Predicting the storms of the future.
This just in, America. Things are brewing up inside sunspots. There'll be a high-energy burst of X-rays flowing from the sun. For you people on the moon, SPF 3000 will come in handy as the pulse should be hitting moon base Norbert right now.
Solar storms have caused disruptions in our communications and power supplies. For instance, in 1989, a solar storm knocked out electric power in Quebec, Canada. 6 million homes were without power for 9 hours as a result of magnetic solar storms.
Predicting solar storms has huge benefits to us here on Earth. If power companies could receive earlier storm alerts, they could minimize damage and power outages.
So what is NASA doing to warn us about these solar storms?
To learn more about the Sun-Earth connection and how it affects us, I'll show you a really cool website you can do at home or at school.
In the meantime, I'm going to head to NASA Goddard Space Flight Center in Greenbelt, Maryland, to talk with astronomer Dr. Sten Odenwald. He runs Ask the Space Scientist with NASA's Image satellite program.
What are some forms of electromagnetic radiation?
How can satellites help researchers monitor the sun?
Why is it important to track solar storms as they approach the Earth?
If you want to get a clear view of what the sun's doing, you have to get above the Earth's distorting atmosphere. So we use satellites to gather the data that we need to understand how the sun works. The sun radiates at all energy levels. Radiation is energy that travels and spreads out as it goes. There are different types of radiation. Let me show you. Visible light that comes from a lamp in your house, or radio waves that come from a radio station, are two types of radiation. Other examples of radiation are microwaves that cook popcorn in a few minutes, infrared light, which restaurants use to keep food warm, ultraviolet light, which causes our skin to burn, X-rays, which help doctors look at your bones, and gamma rays, which are emitted from radioactive materials. So Jennifer, let's apply this information to the sun. As Eric stated earlier, the photosphere emits energy primarily in visible light, while the lower corona emits energy in extreme ultraviolet light and the upper corona in X-rays. By zeroing in on one particular light energy, we can study the various parts of the sun and how they interact.
Okay, Dr. Odenwald, how can satellites help us to monitor and observe the sun?
With satellite technology, you can look at the sun 24 hours a day. We can put satellites outside of the Earth's atmosphere to collect valuable data from the sun and to act as early warning devices against solar storms. 3 important satellites that monitor the sun and provide us with real-time data are the SOHO, ACE, and IMAGE satellites. If you'd like to learn more about the SOHO satellite, Dr. Terry Kuchera, one of our researchers at NASA Goddard, has all the information.
Great, great. Hey, Terry.
Hi, Jennifer. SOHO, or the Solar and Heliospheric Observatory, has a dozen different instruments which observe the sun 24 hours a day without interference from the Earth's atmosphere. These instruments record the activity of a solar corona, the photosphere, and even study the sun's deep interior. SOHO has telescopes on board that take pictures of the sun in ultraviolet light. Also, SOHO can give us a 2 to 3 day early warning of coming solar storms that can affect the Earth's magnetic field.
That's really cool. Thanks, Terry.
Oh, you're welcome.
So what's next, then?
The second satellite is ACE, the Advanced Composition Explorer. ACE operates like an ocean buoy that measures the density, temperature, magnetism, and speed of the solar wind as it passes by. If a solar storm is headed our way, ACE will detect it and give us 30 to 45 minutes warning that a storm is about to hit the Earth.
Cool. So how do NASA researchers then analyze and interpret the data?
Well, one way we can analyze and interpret data is by graphing. The graph shows the speed of the solar wind changing as it blows by the ACE satellite. The title of this graph is Solar Wind Speed. The horizontal axis, or x-axis, represents the number of days in September of 2000. And the vertical axis, or y-axis, represents the speed of the wind in kilometers per second.
Okay, Sten, it looks like the speed of the solar wind ranged from 350 kilometers per second to 800 kilometers per second during the month of September.
You're right, Jennifer. On September the 18th, the solar wind reached speeds of 800 kilometers per second, or about 1.7 million miles an hour. But most of the time, the solar wind averaged around 450 kilometers per second. From the analysis of this graph, we can determine how long it took the solar wind to reach the Earth's atmosphere.
That's amazing, Sten. Now, besides SOHO and ACE, you mentioned a third satellite, IMAGE. Is that the one you're working with?
That's right, Jennifer. IMAGE, which means Imager for Magnetosphere to Aurora Global Exploration. And it's a satellite that orbits the Earth and measures the locations and changes in the invisible clouds of particles that surround the Earth in space. You probably already know one of these cloud systems, the Van Allen belts. Astronauts and satellites avoid these belts because of their radiation hazard. There is also a separate collection of particles called the ring current, which appears and disappears whenever the Earth gets whacked by a solar storm. Another one of these clouds, called the plasmasphere, is actually a part of our own atmosphere. It extends over 10,000 miles above the Earth. The IMAGE satellite lets us watch these different families of clouds change. IMAGE helps us understand how solar storms can cause problems for our technology in space and the health of our astronauts working there too. More importantly, it helps scientists improve our ability to forecast space weather.
Wow, I realized the sun was critical to sustain life here on Earth. But I guess I never realized the devastating effects the sun could have on us.
It's amazing, Jennifer. Solar storms have caused billions of dollars worth of satellite damage in the last 20 years. They have caused blackouts and will always be a hazard for astronauts working in space. Satellites like SOHO, ACE, and IMAGE, and their replacements, will be our only means of keeping track of when the next storm hits Earth's magnetic field. If students would like to learn more about how the sun works and about solar storms, they can visit the Sun-Earth Day website, which was developed by the Sun-Earth Connection Education Forum, in collaboration with the NASA Office of Space Science.
Thank you so much, Dr. Odenwald. You know, Dan has been working on some websites about the sun. Let's go see what he's up to.
Welcome to My Domain. We've got a cool activity on our NASA Connect website to help you explore problems related to solar weather. It's a PBL, or problem-based learning activity. Here's the problem you and your classmates will try to solve. You are the secretary of your club and have used a pager and a cell phone to let your committee know about the time for your next meeting. When no one responded, you made several calls the next day and found that no one got your messages. You want to find out what went wrong. Go to Dan's Domain on the NASA Connect website to find out more about how to solve the problem. You'll also find a link to NASA Goddard's Sun-Earth Connection Education Forum. Here, you'll find a lot of great resources to help you in your exploration. One of the resources is a guide to space weather. In it, you'll see images and information about such things as sunspots, solar cycles, solar flares, auroras, and more. Check out the links to the Eclipse Archive. It gives detailed information for all eclipses of the sun and moon from 2001 through 2005. And teachers, there's an excellent educator's guide that you can download from the website. This guide is designed to provide educators with a quick reference to materials and resources that are useful for understanding sun and earth connections. The web-based activity I've just talked about could be used for collaborating with other NASA Connect classrooms around the world. ePals.com has a website that provides a meeting place and collaborative tools that over 4 million teachers and students can use to connect with other classrooms and work on projects like this together. All you have to do is have your teacher create a profile for your class. Make sure to include the keywords NASA Connect in your profile. By using ePal's search tool, your teacher can easily find other NASA Connect classrooms. You'll also find free teacher-monitored email for students, as well as collaborative tools like moderated discussion boards and chat rooms. That's it for my domain. Now back to the Maryland Science Center.
Okay, let's review. We've learned about the basic parts of the sun. We've learned how research scientists study the sun with different types of light radiation.
We've also learned that satellites provide us with this information.
Right, but what if we could see the events leading up to solar storms? Dr. Michelle Larson from the University of California at Berkeley has the scoop.
What is the goal of the HESSI satellite?
When do solar flares occur on the sun?
How do solar flares have a direct effect on the Earth's atmosphere?
Hi, I'm Michelle Larson, and I'm an astrophysicist. An astrophysicist is a researcher who studies physics in space. I'm here at Vandenberg Air Force Base in California with the HESSI satellite. Let's take a look. HESSI, or High Energy Solar Spectroscopic Imager, is designed to learn more about the basic physical processes that occur in solar flares. Teams of astrophysicists and engineers work together to decide what kinds of observations HESSI will make and what kinds of scientific instrumentation will be required. The HESSI teams will achieve their goals by taking pictures of solar flares in the X-ray and gamma-ray radiation range.
What is a solar flare?
Well, remember when Eric told you that solar flares are the biggest explosions in the solar system? A solar flare occurs when magnetic energy that builds up in the solar atmosphere is suddenly released. Charged particles, such as electrons, protons, and heavier ions, travel away from the sun along magnetic field lines. Others move towards the surface of the sun and emit X-ray and gamma-ray radiation as they slow down. Flares produce all forms of radiation, from radio waves and visible light to X-rays and gamma rays.
Why study solar flares?
The biggest flares are as powerful as billions of hydrogen bombs exploding at the same time. We still don't know what triggers them or how they release so much energy in such a short time. But solar flares have a direct effect on the Earth's upper atmosphere. For instance, long-distance radio communications can be disrupted by the effect of flares on the Earth's ionosphere that is a part of the Earth's atmosphere. In addition, energetic particles accelerated in solar flares that escape into interplanetary space are dangerous to astronauts outside the protection of the Earth's atmosphere and magnetic field, and also to electronic instruments in space.
Where do solar flares occur?
Solar flares occur in the solar atmosphere. Inside a flare, the temperature is roughly 10 times hotter than the corona and can be as high as 100 million degrees Celsius. The frequency of solar flares varies with the 11-year solar cycle. At solar minimum, very few flares occur. As the sun approaches the maximum part of its cycle, they occur more and more frequently. Let me show you on this graph. Let's look at the graph of actual solar flare data from 1990 to 2001. The title of this graph is Number of Solar Flares versus Years. The horizontal axis, or x-axis, represents years, and the vertical axis, or y-axis, represents the total number of flares recorded. From the graph, we can see that we have a solar maximum in 1990 and one in 2001. We have a solar minimum at some point between 1995 and 1996. This graph shows us that the sun does have a solar cycle, which is about 11 years. From this graph, we can predict when the next solar maximum and minimum will occur.
How do you study solar flares?
Well, it's actually very difficult to study the high-energy X-rays and gamma rays emitted during solar flares. To solve this problem, HESSI uses a very unique method. HESSI will obtain pictures of solar flares within the X-ray and gamma ray range by using pairs of metal grids to cast shadows onto detectors. Each grid is a bit like a fine screen, but with lines running in only one direction, like jail bars. The solid slats block radiation, and the open slits allow radiation to pass through. As the satellite rotates at about 15 times per minute, the grids will allow high-energy X-rays and gamma rays from different parts of the sun to sometimes pass through and sometimes not, depending on how the slats are oriented. The HESSI detectors will measure the energies of the X-rays and gamma rays that get through and will record how things change as the satellite, and therefore the grids, rotate. This is enough information to figure out where the radiation came from on the sun. This information will be transmitted to the ground, where HESSI scientists will use it in their computers to make pictures of flares in X-rays and gamma rays. It is like putting together the pieces of a puzzle to figure out what the picture is. The special way HESSI will measure high-energy radiation from the sun, combined with the way scientists will analyze the data, will allow us to study the sun in a way never before attempted.
Why will HESSI observe the solar flares in the X-ray and gamma ray range?
We know that light emitted in the X-ray and gamma ray range shows different events than that emitted in the visible light range. High-energy X-rays and gamma rays carry the most direct information available about the energetic particle activity on the sun that occurs in solar flares. With the help of HESSI, we will be able to anticipate solar flares, and HESSI will aid in understanding energetic events throughout the universe.
Thanks, Michelle. Say, how would you like to plot out the cycles of solar flares? Students at Hardy Middle School in Washington, D.C. will show you how. Check out my nose.
Hi, we're from Hardy Middle School.
Here in Georgetown, Washington, D.C.
NASA Connect has asked us to show you this hands-on activity.
It's called X-ray candles. Solar flares on your birthday. Here are the main objectives.
You'll discover the solar cycle through an investigation of solar X-ray flares. You'll record the total number of flares in your birth month over an 11-year period. You'll compute the percentage of M-class flares that occur. You'll graph your findings to help you identify the long-term pattern of flare activity on the sun. And you'll incorporate problem-solving strategies in a real-life application. The list of materials you'll need for this activity can be downloaded from the NASA Connect website. The class will be divided into groups according to their birth month. Teachers will provide each group with solar flare data for the corresponding birth month, and each student with a calculator, graph paper, and student data charts.
Good morning, class. Today, your job is to plot and analyze solar flare data from a satellite and determine the solar cycle of the sun.
First, add the total number of flares that occurred in your birth month for each year. Record that number in the last column of each row of the solar flare data sheet. Second, add all the numbers in the last column of the solar flare data sheets to determine the total number of flares in your birth month for each year. Record that number for each year in the box at the bottom of each page of the solar flare data sheet. Next, add the total number of M-class flares in your birth month for each year. Record the total number of M-class flares for each year in the box at the bottom middle of each page of the solar flare data sheet.
What do you get for your birth month? 14.
Groups will need to collaborate with each other to get information on the total number of flares and M-class flares for all months in each year. Record the data on the student data chart. Record the total number of flares and M-class flares for each year on the student chart. From this data, compute the percentage of M-class flares for each year by using the equation M-class flares divided by total number of flares multiplied by 100. Students will then plot the percentage of M-class flares versus year.
Okay, why is it important for researchers and scientists to know when solar maximums and solar minimums will occur? Connor.
So they know when solar storms will hit the Earth.
Anybody else? Allison?
So they can warn us if the electricity will go out in our homes.
Special thanks to the AIAA National Capital Section and the AIAA mentors from the University of Maryland who helped us with the show.
Thank you. We had a great experience. And we encourage teachers to visit our website to learn more about the AIAA mentorship program in your area.
Well, that wraps up another episode of NASA Connect.
We'd like to thank everyone who helped make this program possible.
Got a comment, question, or suggestion? Well, email them to connect@lark.nasa.gov.
Or pick up a pen and mail them to NASA Connect, NASA Center for Distance Learning, NASA Langley Research Center, Mail Stop 400, Hampton, Virginia, 23681.
Teachers, if you would like a videotape of this program and the accompanying lesson guide, check out the NASA Connect website. From our site, you can link to the NASA Educator Resource Center network. These centers provide educators free access to NASA products, like NASA Connect. Or from our site, you can link to CORE, the NASA Central Operation of Resources for Educators.
View this and past NASA Connect shows on your computer. Visit NASA Quest at quest.nasa.gov.
So until next time, stay connected to math,
science,
technology,
and NASA.
See you then.
Bye.
Our star, the sun, is a big ball of gas, and it's 99% of our solar system's mass. It's an average star in our Milky Way, warming the Earth every day. What powers our sun and makes it so bright? Come on and tell me what makes all that light. Hans Bethe long ago reached the conclusion it changes hydrogen to helium by nuclear fusion. When fusion takes place, light is created and it makes its way up,
although rather belated,
through the photosphere. That's the part that we see. The light comes out and shines on you and me.
About a million Earths could fit in the sun,
but if you were there, you wouldn't have much fun. It's 6,000 degrees at the photosphere,
and much hotter inside the solar atmosphere.
There are a few places where it's not so hot,
like at the center of a big sunspot.
But heat is relative, it's still pretty warm.
Sitting on a sunspot would do you great harm. Galileo discovered sunspots. One of those things that's funny does. They're cooler parts, scientists feel, caused by a stronger magnetic field. The spots move around the face of the sun, proving to all solar rotation a strange kind of movement to do a full roll.
25 days in the middle, 36 at the pole.
What about flares? I've heard of them here, like giant explosions in the chromosphere. The magnetic fields above the sunspots reconnecting again after being in knots. Above the chromosphere, the corona is placed. It's millions of degrees and reaches way into space. It's very thin, but read my lips. That's the part that you'll see in a solar eclipse. That's the end of our song about Mr. Sun. We hope that you find that learning is fun, but never look at the sun. You could